There is a technology for installing pipelines without the hassles of open-cut trenching. A system that works unobtrusively, below the Earth's surface. It's a fully remote-controlled technology, keeping workers out of harm's way, with built-in safeguards to prevent surface subsidence and heave, and yielding an accuracy of plus or minus 1 inch in line and grade. This revolutionary technology is called microtunnelling. Iseki, the world's leader in microtunneling technology, welcomes you to this, the future of underground pipe installation. Microtunneling is a technique for installing underground pipe without trenching. Powerful hydraulic jacks are used to push specially designed pipes through the ground behind a remote-controlled tunneling shield called a microtunnel machine. Simultaneously, excavation takes place at the front of the machine, and the excavated materials are pumped to the surface by a circulating slurry system. Microtunneling is distinguished from other tunneling techniques by 4 very important factors. Microtunneling is a remote-controlled operation, reducing manpower requirements and increasing job site safety. Earth pressures at the tunnel face are counterbalanced by the machine, virtually eliminating ground movements. When groundwater is present, hydrostatic pressures are counterbalanced by the tunneling machine without dewatering. And microtunnel machines can be designed to perform in the widest possible range of soil conditions with the same cutter head. Microtunneling systems permit tunneling through almost any ground, while providing maximum security against ground movements without the employment of costly ground stabilization or dewatering techniques. The end result is a flexible, hardy, watertight finished pipeline with an absolute minimum of surface disruption. The microtunneling process begins with careful planning. A full site investigation report is undertaken to determine the characteristics of the soils likely to be encountered, together with details of any water table. All other aspects of the project are examined, such as the tunnel's length, depth, diameter, and route, the type of pipe to be installed, surface characteristics, and any other factors that are relevant to the particular project. All of these variables are carefully considered, and an optimum plan is identified. The first stage of construction calls for shafts to be sunk at each end of the intended drive, usually at manhole positions. On one end, a drive shaft, and on the other, a reception shaft. The drive shaft marks the beginning of the drive. The drive shaft may be circular, oval, square, or rectangular, but it must be long enough to accommodate the tunneling equipment, specifically the combined length of the thrust wall, hydraulic jacking system, microtunnel machine or pipe, whichever is longer, and entrance ring. The reception shaft, on the other hand, need only be large enough to accommodate removal of the microtunnel machine. There are several different methods of shaft construction, including sheet piling, liner plate, soldier piles and sheeting, corrugated metal pipe, segmental lining, precast or cast in situ caissons, and shallow trench-sheeted or timber-supported excavation. In some cases, ground treatment may be required to permit shaft construction. Ground treatments include well pointing and deep wells, chemical stabilization, and in very difficult conditions, ground freezing. The method of shaft construction is often determined by the specific requirements of the project. However, contractor preference, economics, and ground conditions also play major roles. After completion of the shaft walls, final preparations to the drive shaft consist of pouring a concrete base slab to support the tunneling equipment, constructing a thrust wall when necessary to provide a reaction against which the pipe is jacked, and installing an entrance ring through which the microtunnel machine and pipe will pass as they enter the earth. Depending upon the ground conditions, measures such as ground treatment or grouting may be required immediately outside the entrance ring to prevent ingress of ground during launching of the microtunnel machine. Once the drive shaft has been prepared, the microtunneling equipment, which is thoroughly tested before delivery to each project, is transported to the drive shaft and assembled in position. The microtunneling equipment includes the operation cabin and remote control board, the jacking and lubrication systems, the slurry system, as well as ancillary equipment such as cranes, generators, and trucks. Then the microtunnel machine, the real workhorse of the microtunneling process, is lowered into the drive shaft and onto the guide rails. Different types of microtunnel machines are available to cope with a host of ground conditions. Machines are available in a wide range of sizes, in diameters from 12 inches to 12 feet and beyond. Once the microtunnel machine is aligned on the guide rails, which have been set to the required line and level, all cables and hoses are connected to the machine, and the total system is tested once again. The drive begins, and the microtunnel machine is thrust forward by the hydraulic jacks, first passing through the entrance ring, then tunneling through the ground on its journey to the reception shaft. Powered by electric motors, the rotating cutter head cuts through the earth. Excavated material is crushed in the head of the machine when necessary and passes into a slurry chamber, where it is mixed with slurry and transported to the surface via slurry pipes. During excavation, a sophisticated earth pressure counterbalancing system is employed. By maintaining a consistent counterbalance pressure on the tunnel face, always between the active and passive earth pressures, ground movements are virtually eliminated. After the machine has fully penetrated the ground, excavation is halted, cables and hoses are disconnected, and the first section of pipe is lowered onto the rails. The pipe is pushed up to the back of the microtunnel machine, where they are joined by an adapter ring, and all systems are reconnected. Then, together, they are jacked forward as the excavation at the face of the machine continues. On the completion of the jacking of one pipe, excavation is stopped. The jacks are retracted. Another pipe section is inserted behind it, then pushed forward, and the process is repeated until all the pipes are installed, forming the permanent tunnel lining. The alignment of the machine and pipe is controlled using a laser-guided steering system. A laser beam originating from a laser at the rear of the drive shaft and set to the required line and grade is projected onto a target mounted inside the microtunnel machine. An image of the target is captured by a TV camera and relayed to a monitor in the remote control board at the surface. The operator can activate hydraulic steering jacks inside the microtunnel machine as necessary to articulate the front section of the cutter head and alter the attitude of the microtunnel machine. Accuracies of plus or minus 1 inch in line and grade are typically achieved over an entire drive. The slurry system performs two functions. It removes the excavated spoil, and it counterbalances any groundwater. The slurry system consists of a closed pipeline loop, which circulates the slurry mix through the head of the microtunnel machine, where excavated materials are picked up into suspension, carried out of the tunnel, and deposited into settling tanks on the surface. The slurry is pumped through the system by a number of electric pumps. Flow to the microtunnel machine is provided by charging pumps. Flow from the microtunnel machine back to the surface is provided and controlled by variable speed discharge pumps. A pit bypass unit provides a means of reversing the flow in order to clear any blockages or to disconnect the lines. When excavating cohesive soils, the slurry may be plain water, perfectly suitable to carry clays and silts. In sandy or granular soils, a thickening agent, such as bentonite, possibly with the addition of polymers, is added to the water to increase its density and viscosity and act as a support medium to carry these denser spoils to the surface. The slurry and excavated materials are separated at the surface in settlement tanks, or in some cases for large machines, by a system of vibrating screens or hydrocyclones together with settlement tanks or lagoons. The cleaned slurry is reused in the circuit, and the spoils are accumulated for subsequent disposal. The slurry system serves a second very important purpose. Where groundwater is present, the slurry pressure at the face of the microtunnel machine is used to counterbalance hydrostatic pressure in the ground, thereby eliminating the need for dewatering. Pressure sensors inside the microtunnel machine measure both the groundwater and slurry pressures. A crossover system and shutoff valves, together with the slurry pumps, provide a means of adjusting the counterbalance pressure as necessary. The crossover system and shutoff valves are also used to suspend flow through the slurry chamber on the introduction of each pipe and at the end of each day's work. Pipe used in microtunneling, called jacking pipe, is basically a thicker-walled version of direct burial pipe. Jacking pipe consists of a female end fitted with a collar and a thin ring of fiberboard to act as a packer, and a male spigoted end fitted with a rubber seal. When joined together, a durable, watertight seal is formed. The outside surface of the pipeline is smooth, minimizing friction as it is jacked through the earth, and the fiberboard packer cushions some of the load between pipe ends, reducing the potential for local crushing of the pipe material. Concrete, FRP, and vitrified clay are the most common formulations of jacking pipe, although steel and ductile iron are also used. Jacking pipe is available with inside diameters ranging from 6 to 120 inches and section lengths from 4 feet all the way up to 40 feet. The hydraulic jacking system provides the thrust required to move the microtunnel machine and pipe through the earth. Jacking systems are available in a wide range of sizes, capacities, and configurations, from 200 tons up to 4,000 tons. The hydraulic jacking system is located at the rear of the drive shaft. After a section of pipe is placed on the guide rails, the jacks are slowly extended, powered by an hydraulic power pack on the surface. The force of the main jacks and the speed at which they extend is carefully synchronized with the excavation rate of the microtunnel machine. A thrust ring and pipe ring adapter ensure that uniform thrust is transferred from the jacks to the pipe. Thrust at the rear of the jacks is transferred to the thrust wall through pressure plates. Jacking systems can be either long-stroke jacks, jacking a complete pipe length in one push, and normally requiring a larger drive shaft, or, in order to accommodate smaller shafts, short-stroke jacks, together with spacer blocks, and a variety of indexing systems using multiple strokes of short-stroke jacks. These latter two systems achieve the same goal, pushing an entire segment of pipe while consuming smaller footprints and permitting smaller-sized drive shafts. The jacking force required to thrust the pipeline forward is mainly a function of frictional forces built up around the pipeline. This load depends on many factors and is generally calculated based on the square footage of the external circumferential area of the pipeline. As the length of the drive increases, so does the total friction produced between the pipe and the earth, thus demanding a greater jacking force. To reduce this friction, a clay-based or polymer lubricant mixed in a lubricant mixer on the surface is injected into the annulus between the pipe and the surrounding earth. Lubricant is always introduced immediately behind the microtunnel machine through a lubrication port in the machine. For larger machines and longer drives, lubrication ports are also provided at regular intervals through the wall of the jacking pipe to provide continuous lubrication around the pipe. This technique results in a considerable reduction in friction. Thus, the required jacking force is reduced, and longer jacking lengths are achievable. However, at some point during a relatively long drive, the required jacking force may exceed the capacity of the main jacking system, or the structural capacity of the pipe or thrust wall, requiring the introduction of one or more intermediate jacking stations, or interjacks. These interjacks provide additional jacking capacity and redistribute the total required jacking force at regular intervals along the length of the pipeline. Interjacks consist of a number of smaller hydraulic jacks assembled around the inside surface of an interjack canister. Interjacks are placed between sections of pipe and moved forward with the pipeline in the normal way until their operation becomes necessary. At such time, the first interjacks are opened, thus moving forward the microtunnel machine and the front section of the pipeline. Then the main jacks in the drive shaft are actuated, causing the closure of the interjacks while advancing only the rear section of the pipeline. This sequence is repeated for the duration of the drive, and upon completion, the interjacks are removed and the pipeline closed up, leaving in effect a standard pipe joint. A highly trained operator carefully monitors and controls all aspects of the microtunneling operation from within a control cabin on the surface. The operation board displays data and provides control of all mechanical systems. Operation boards can be standard with manual steering and data recording, or can provide fully automated computer-controlled steering and data logging. Other workers handle such duties as pipe and spacer placement and cable and hose connections. Normal site operations are 8 to 10 hours per day, 5 days per week. Only in extraordinary circumstances does it become necessary to increase operations to 24 hours per day. As the microtunnel machine nears the reception shaft, excavation is halted temporarily, and if groundwater or soft ground is present, an exit ring is placed on the wall of the shaft. Finally, the microtunnel machine exits the earth into the reception shaft, completing the drive. After the drive, the microtunnel machine and equipment are removed, manholes are built, and the shafts are backfilled. Microtunneling projects often consist of several drives. In such a case, 2 drives are made from each drive shaft, in opposite directions, so that only the jacking equipment need be turned around to start a new drive. This process is repeated at every other shaft, ultimately forming the whole sewer or pipeline. Microtunneling is a proven alternative to open-cut trenching and open-face tunneling techniques. It is the ideal solution for minimizing surface disruptions, avoiding utility conflicts, lessening the risk of ground movements, and minimizing hazards for workers, traffic, and pedestrians. Microtunneling is the preferred choice for deep sewer and pipeline installations, and where these are beneath congested urban and environmentally sensitive areas, where surface disruption is unacceptable, and where there are difficult ground conditions or a high water table. Since 1974, nearly 2,000 Iseki microtunnel machines have been manufactured, and many thousands of miles of pipe have been driven worldwide. Iseki is proud to be the world's leader in microtunneling technology, and is proud to welcome you to the future of underground pipe installation.